您学者，请起出盖口。
Let's wait for a few minutes. 生病，生病。All right. So there's one last theorem we're gonna do for this whole course here is Arzela-Ascoli theorem. Okay, Arzela-Ascoli theorem. We will do one version on the compact metric space, and then the other version on the general general topological space. If we can finish Arzela-Ascoli theorems today, then tomorrow we will have master presentations, and then hopefully we can discuss assignment 5, 6, 7. I will return to you. Yeah, and then 8, 9, 10. I'm still waiting some of your submission. Okay. Right. So last week we talked about how can we comment on compactness of continuous function space. Right. Okay, we know that if it is Rn, right, we know that Rn, a subset of Rn is compact if and only if it is closed and bounded. Okay, so we want to obtain a similar criteria to talk about a subset of continuous function space to be compact. Okay, so to do that, obviously we need to make our continuous function space to be a metric space. Okay, so let's define a metric on it. Where's my metric? All right. So briefly speaking, last week we have defined a supremum metric on continuous function space here. So basically, you just check f the distance between f and g at every point x. Okay, so because fx and gx is something in the metric space, it should be in the metric space. So I think it's better that I write here. And y the metric space. Okay, then you can evaluate your f and g at x so that you get some point in the metric space and then compute the distance there. Then you get the supremum. But supremum doesn't make sense if the distance could go arbitrarily close to infinity. Okay, so we require x to be compact because we know that continuous image of compact set is compact, which means in general case it's totally bounded. Okay, so this then if you consider the open ball generated by this metric here, then this gives a uniform topology. So mind you, this matrix here is evaluating on two functions. If you want to evaluate two functions, you really need to check at every point. So the ball is like a drawing on the function, on the side of function. Okay. So one could check that convergence with respect to subnorm here is equivalent to uniform convergence. Okay. So uniform convergence is the one tracking absolute. Okay, so there's another way to get a uniform topology here actually. Okay, where you consider the supremum of this bounded metric here. Okay, so either either you take the distance of 2 points or you take one minimum of them. Okay? So meaning you cannot go arbitrarily larger, okay, in this case here. So in this case, then we don't have the x to be compact problem here because our metric here is always a bounded metric. Okay, but the key here is that they define the same topology. Okay, the ball is equivalent, sort of speaking. Okay, right. So I think we want to do this Arzela-Ascoli together. So what's this simple version of Arzela-Ascoli here? I think I introduced this in my MA1 class, but we didn't prove it. So we left it to general topology right to the end. Now, okay, to do this. So a little bit general than what we have in the MA1. Okay, so here we just consider X to be a compact metric space. Okay, then we claim that a subset F of continuous space from X to Rn. So the codomain is a Euclidean space with the submetric is compact if and only if. So similar to the compact Euclidean Rn space. So first of all, it has to be closed. Okay. Next, bounded, but the bounded here is uniformly bounded. Okay, because you are no longer talking about 2 points, right? Points being bounded, but you need to talk about a function being bounded. Okay, you want to bound every value. And lastly, the most important thing that we discuss in this subtopic here is equicontinuity. Okay, hello. Okay, so equicontinuous, if you still remember, right, it is a epsilon delta condition that can control every function. Okay, control every function inside the set. Yeah, so it should be the same epsilon that can check continuity at every function. Okay, if you still remember. That is the quantifier for all f in the script f, right? Appear in the middle, right? Okay. Yeah. Okay. So let's do this. So actually one side is easier. Okay, so compactness imply the tree condition is easy. Why? Wait, let me see. Which one is easy? Yeah, this one should be easier. So basically, a compact set in a metric space. Okay, we know that it's already a metric space, right? Immediately implies what? Immediately implies that it is closed and bounded. Okay, so obviously the bounded here need to be corresponding to the matrix that we introduced. But just now we say that the submetric has something to do with the uniform metric. So there's some relation there. So the only thing to show is show that this F is equicontinuous. So it suffices. Show that F is equicontinuous. Hello. So to this end, maybe we will use a contradiction. Okay, suppose on the contrary that F is not equicontinuous. Okay, so if it is not equicontinuous, then you just throw out the negation. So the negation will be there exists an epsilon greater than 0 such that for all n in n, there exists an Sn Yn in X and also Fn in F such that d of Sn minus Yn is less than 1 over n, but Fnx minus Fny to be greater or equals to epsilon. Okay, but then what? But then you have what have you created? Actually, you have created a sequence of Fn that have no convergent subsequence. Okay. If this case hold true, then you have created a sequence that doesn't have a convergent subsequence. Okay, so for example, for every epsilon greater than 0 and epsilon delta greater than 0, you just pick nj to be greater than 1 over delta. Okay. I think this is also the trick that you use in your tutorial, right? I think I just finished marking the Cauchy. You say that what's that question now? Seemingly long question. Tutorial assignment 7, question 2. About what did I ask you to do in that question? I just give you back, right? Can't remember. What's that question? You also use this technique, right? Show that there's no convergent subsequence. I suddenly cannot remember. What's that question? Yeah, compactness doesn't imply sequential compactness, right? Okay. Okay. Yeah. But in this case, we have metric, right? So we have equicontinuity. So there's some sequence we will cook up here. And then we show that there's no convergent subsequence. Okay, how about the other direction? Okay. So the other direction, we want to show compact, right? Okay, so to show compact here, we can use the equivalence definition, okay, which we just proved that F is complete and totally bounded. Okay, so totally bounded here is a very technical thing. Later you will see. But this technical thing is what the analysis always use, in particular in ODE or PDE to get your solution. Okay, so we'll see how we prove totally bounded here. So completeness, I think, is pretty straightforward, sir. Okay, why is it complete? Okay, because we already know that it is closed. Okay, but obviously you need to prove that the continuous function is complete. Is this what we did in the assignment? What's the thing we show is complete? I think it's assignment 8. Did we do? What are we showing complete there? Then I asked a bunch of complete. Is it complete or yes, you remember I gave you a lot of Cauchy sequence or what like? Okay. L infinity is complete under L infinity. Okay. So I think this is what we know, right? So this space with the sup norm is complete. Okay. So F is complete because we know that it is closed, and then we know the whole space is complete. So it is complete. Closed in complete is complete. Let me check. Let me quickly check. Timeline 8. I just asked you to check the sequence of real number. So similarly, I think you can show that this F here is complete. Wait, so there's one easy way, not talking about writing all the details, but there's one important concept why is complete is if you are taking sup norm, right? Just now we say that it's equivalence of the uniform convergence. So let me ask you, your uniform limit of a continuous function is continuous. Yeah, there's something that we learn in MA1. Uniform limit of a continuous function should be continuous. Okay. Yeah. So imagine that your convergence is uniform, meaning at every point, right, the epsilon delta that you use is the similar. So why not continuous? Cannot do much. Okay, you cannot like becomes not continuous at certain point, right? So because uniform like will control like every point equally. That's what the uniform means, right? Everyone wear the same uniform. Okay, so either you tall, you short, right? You wear the same uniform. Okay. Hey, I cannot find my file. Where is it? Okay, right. Second, let's prove about total boundedness here. So the total boundedness here is very interesting. This is one of the way that we can approximate function. Yeah, I didn't write out the full details, but I already like summarized a bit. So suppose that delta is greater than 0. Okay, so we want to fix the radius of the ball, right? And then we said that there's only finite how many ball can cover your F. So what do we need to find here? So basically, we need to find a finite set X of function. Okay, in this case, it's a finite set of function in the space we want to consider C from X to Rn, such that okay, for every F in script F here, and there's some Xi such that if d of xxi less than delta, why do I put delta 1 here? I think delta. Then this would imply that fx minus fxi is less than delta over 4, let's say. Hey, sorry, I'm a bit stupid here. So this one is a wrong one. So for all f in f, there exists g in x such that sup f minus g is less than delta. Okay, this one makes more sense. Okay, so within the delta ball here, okay, you just need a finite many g to do that. Okay, so there are few steps we lay out at 1, 2, 3, 4. Okay, so there are basically 4 steps to do that. So first, okay, since we know that f is bounded, then actually we can get bound for all the fx. Okay, so we're gonna use all the criteria given. So first, we have a bunch of f, right? Okay, now I kind of bound all the fx. Okay, I squeeze the fx into one region. Okay, let's say this is k. Okay, from minus k to k. So all the f live inside k to minus k only. Okay, then we slowly bound everyone. Okay, so we already bound them in the region of k to minus k. Then next, we'll use uniform equicontinuity. Okay, maybe you want to ask, hey, why your equicontinuity upgrade to uniform equicontinuity? Basically, this is how you upgrade continuity to uniform continuity because we have a compactness here. Okay, so we're gonna choose delta 1 greater than 0 such that for all uv in x, and then for every f in f, okay, d of uv less than delta 1, what implies that fu minus fv is less than delta over 4. You see, there's a delta over 4 appears here. What do you think? Huh? Sorry? Yes. So how many of them do you think? Four. There's 4 parts to bound here. Yeah, so let's see what are the 4 parts here. So we already bound one of the part, okay? Just Fu over Fv. Later, we'll see where the other 3 parts come from. Okay, so next, we will use total boundedness of x. Okay, this one is of x itself because we want to prove for the function case. But we know that x is compact, so also totally bounded, right? So now we will use the domain to be totally bounded. So in this case here, what does it mean? This means we don't only need to care a finite set of points in x. Okay, we just need to care a finite many point in x so that we can already cover everything in my domain here. Okay, so how to control here? So here we'll control it by dx xi less than delta 1. Then this will implies that fx minus fxi to be less than delta over 4. Okay, so this is the second delta over 4 here. Okay. So first delta over 4 happens at every f, and then random uv, okay, random uv. But the next one is random uv I link to the total bounded, the xi coming from the total boundedness of xi. Okay. Better there's a very nice picture how we put all these together. So let's wait for it. So this is the second one. 1, 2. Okay, let's do a third one. All right. So the next one is quite how to say, quite random, quite arbitrary here. So we choose a finite set of point in codomain as well. Okay, we didn't claim that it's totally bounded, but we pick it. We pick these finite point so that if y is in Rn, and we also know that the value of y is bounded by k, we just need to care about points bounded in this k region here. Then there exists yj such that y minus yj is less than delta over 4. So what does this mean? Although we know that Rn is not compact, so it's not totally bounded, but the place we care from minus k to k is really compact, right? Minus k to k is really compact. Okay, so we have totally bounded on our image, sort of speaking. It's not the core domain itself, but just image. Okay, so we have two sides to be totally bounded. So meaning only finitely many points, then I can see what happens in the surrounding. Okay. All right. So what we do here, what do we do next? Next, we're gonna do, let's consider this two finite set. Okay, so how do we care about this two finite set? So we have a finite set on the domain already. Now we also pick a finite set for the codomain. So now we consider set of all functions. Okay, all functions alpha from x1 up to xp to y1 up to yq. Okay, you might think that, oh, this is like a combinatorics question. P point to q point. How many kind of function you can define on this two set here? How many? Huh? PQ? P times Q. Actually, no, eh. Uh, so actually it is Q to the power of P. Right. I'm not talking about whether you can repeat or not repeat, right? Yeah. Not necessarily subjective. So it's Q to the P. You can pick again, pick again, pick again. No. You can repeatedly. Everything sent to Y1 also can. Everything sent to Y also. So you count all of these. Yeah, possible case. So it's Q time, Q time, Q time, Q time, Q time, Q time, Q time. Okay. Makes sense. Every P you can have Q choices. Yeah. Okay. So for each alpha here, then what we do is we choose F such that for every I from 1 to P, fxi minus alpha xi here is less than delta over 4. Okay, and then we will label this as G alpha. Can we pick this F? Do you think this F exists or not? Does it exist? Does this kind of F exist or not? Does this F exist? Okay, let me show you the picture first. Let's think about whether it exists or not. So basically it's like this. Okay, so you pick finitely many point here, and then you have some finitely many choice on your codomain as well. So based on this point here, right? The claim here is you can choose F that is close to this point, delta over 4. Does this function exist or not? What do you think? Can you always find such F? It could be empty lah. Maybe it could be empty actually. Can it be empty? Huh? Is delta over 4 arbitrary? Delta over 4 arbitrary or not? Delta over 4 arbitrary. No, what do you mean? No, fixed already. It's fixed one. But remember that xi, how we pick this xi? Xi says that for every f in sorry, how do we pick xi? So for every x in x, there exists xi such that if the point x is delta 1 close to xi, implies that fx minus fxi is less than delta over 4. This is true for all f. Seems like this is true for all f. As it there exists. Huh? Mm-hmm. Closer to the x-axis, what do you mean? I think I missed something, huh? So this line here, huh? Where's this f come from? how should we quantify this f? Is it the axis or for O? Choose a finite point. This one can choose. This one is a finiteness, right? Of x. I think this one is fixed for f, I guess. This one is fixed for f. Okay, fixed for one f. So if you have one f, then for your domain, you can pick finitely many to do this. Makes sense, this one. To fix one f, because f is continuous. Fix an f. If by totally bounded version of x, then you can do this. But then what they? Yeah. So let me see. Does this f always exist or not? Let's think about this. Does this f always exist? So yi are just chosen somewhere in between minus k and k, you see? Okay. And then so the key, the point here is I ask you to I put this graph out. So meaning you see a function from xi to yi here is just a graph like this, right? Okay, like a discrete graph. So the point here is, can I find a function that's delta over 4 close to this point? Could it be empty for some alpha? Is it possible? I think. Is it possible to be empty? Is it possible to be empty? Or does it matter? Okay, I think so. I make a comment here. So okay, let's say we have this G alpha, and then let X be the set of all G alpha here. And then I claim that actually this set is non-empty. Maybe G alpha is maybe some of the G alpha doesn't work, but this whole set here should be non-empty. Okay, here says that by the construction of yi here. So what's the construction of yi? Yi just try to cover everything in between minus k and k. Okay. Yi here covers everything in between minus k and k. Okay, it claims that there's some f must pass through it. Does this make sense? Okay. So then lastly, we will show that for every f in f, actually there exists a g alpha x such that du of f comma g alpha here is less than. Okay. Then I think this g alpha cannot be zero, right? Cannot be empty. There should exist something like that. I think if it doesn't exist, maybe you could do some contradiction to the completeness. Maybe there's some limit that you cannot find if it doesn't happen. Okay, that makes sense. Since this delta is arbitrary, like what you said. So if like for all delta you cannot do that, then there'll be something wrong with the limit thing. Yes. Continuity. You mean the continuity of the function itself? No, my claim is it will contradict the completeness. Why do you think continuity works here? Huh? The point here is the existence of this f. Can I get a f that's delta over 4 close to alpha? The point graph. Okay. My claim is if you cannot find something close to this, okay, then there will be some contradiction to your completeness. Maybe you are missing something inside your space. If you cannot find this curve that estimated. Yeah. Not that this delta here is chosen arbitrarily. So yeah. Okay. So then right. So I think that part need to be written. Let me check. I got the detail now. But if you can find this f alpha here, there's the f alpha. So how are we gonna do this f alpha thing? So how are we gonna do this g alpha thing? So let's see how we should choose it. So how we're gonna bound this distance here is first we will bound this fx using the totally boundedness of x first. Okay, and then this fxi I can estimate using alpha xi. Okay, because what let me see. Let me see, can I bound this? So for each alpha, we can choose f that's close to this. Let me see, let me think. Can we do this or not? Okay, we can do this. Why? Because these alpha xi here are the yi that we pick. Okay, these are the yi that is totally bounded our image. Because fxi is living in the image. Okay, so there's some yi that can cover this xi. Okay, within delta of 4. Okay. So first part is using a totally boundedness of totally boundedness of x. Second, because we choose yi to be bound all the image within delta over 4, then we can continue bound alpha xi here. Then we can bound alpha xi by the construction of g alpha I. So g alpha I is the some other f that's alpha delta over 4 close to this alpha xi. Then finally what? Let me see. Finally, we could do this. We could do the same totally boundedness on x on this g alpha because g alpha is just one of the f. Okay, so how many of them? 1, 2, 3, 4. Okay, so together we have 4 times delta over 4. Okay, which is delta. Okay, so how to choose this alpha? So from this calculation, how to choose alpha here? So that alpha have to pick based on the fxi. Okay, depend on the fxi. Yeah. Okay, so the alpha they choose depend on the fxi. Depend on how you estimate this. Okay. Makes sense. So if you go through this whole argument, basically the key point here is this diagram here. Okay. The key point is this diagram here. Okay. How do you bound the set? So you need to realize on your domain is totally bounded. Okay. So to talk about the real curve here, you just need to pick some finite point from your domain and then finite point from your codomain. Okay, to speak of all these continuous curve here. Okay. How many choices? Q to the P choices is enough. Okay, Q to the P. Make sense? 对吧？ I think this is what you do in the kindergarten, right? 对啊，给你几个点，可以把你线连在一起。Okay, this is a super version of that. Okay, so it's compact. Okay, let's talk about few examples and usage, and then we can take a break from here. So one example is if you look at the family of holder continuous function. Okay, so this one we have discussed last time, right? Moreover, you can show that these functions are uniformly bounded. So meaning for all x, you evaluate your fx, actually is bounded by some number. Okay, uniformly bounded. So meaning 1k will bound everything. So the claim here is holder continuous function is closed, uniformly bounded, and equicontinuous. So meaning it's compact. Okay, so you can do some proof here. Second, Arzela-Ascoli theorem also implies that any sequence from the least strip continuous space function space has a convergent subsequence. Okay. So remember that what's the relation between least strip and holders continuous? Is the exponent there m become 1. Okay. So yeah. So least strip continuous function is compact, but in general, the continuous function, right, that is uniformly bounded is not compact. Okay, it's not compact. Okay, because this guy here, right? This guy is continuous sine function. Okay, it's uniformly bound because at most you go to 1 or -1, top and bottom, but it is not compact. Okay, so there is a sequence such that there's no convergence of sequence. Okay, so really you need to go to least strip or you go to holders continuous. Okay. Yeah. If it is just continuous plus uniform bound is not enough also. You see, here I already chose compact domain. Already I chose a compact domain. So it's not enough. Okay. So Arzela-Ascoli need 3 conditions. So one condition is close. Okay. Second condition is bounded, right? Uniformly bounded. Third condition is equicontinuous. Okay, so something breaks here is because not equicontinuous. Okay, not equicontinuous. But last time we showed that it's equicontinuous. Okay, and then you put uniformly bound. We need to choose it. Okay, we need to fix that. Okay, otherwise it's not uniformly bound maybe. Okay, so similarly for holders, we should bound it as well first. Okay, only then it is uniformly bounded. Okay, you need to add the bound yourself. Okay, last before we go to a more abstract version. So this is a very important theorem for your, I think, ODE. Assume that F is continuous in the open set U. Okay, let T naught and S naught be a point in U. Then there's this H such that the initial value problem here, X prime T equals to F T S T, and the boundary condition is ST naught equals to S naught has a differentiable solution here. Okay. How to use Arzela-Ascoli, where your solution should lies here. How to use Arzela-Ascoli here. So for those who learn more about geometry or geometry, no matter it's differential geometry or algebraic geometry here, S prime T, you should be sensitive about this already. S prime T is what? Is the tangent vector, or then something live inside the tangent space. Okay, so this one tells you the tangent already. Okay, so how do you, so if you want to find the solution, meaning I gave you tangent already at every point. Okay, I tell you boundary condition, where to start. Can you draw a curve out of this tangent line or not? Tangent vector, I mean. Okay. So if in the differential manifold, this is like a floor, okay, you draw a floor. Okay. And then moreover, it requires it to be differentiable. Obviously, it need to be differentiable because at every point I gave you the derivative already. Okay. So how to prove this? So well, if you just use the continuity of f, right, you can write down this solution actually. Okay, this solution. This is like the what do you call that? In MA, what do you call that? The fundamental, fundamental theorem of calculus, FTC. Yeah, FTC. Okay. So your derivative I give you already, integrate it. Okay, so this is what we propose. This is the solution we propose here. Integrate it. Okay, integrate it. I don't know what is it, but integrate it. Okay, and then we claim that this is a differentiable solution. So you need to prove that this is a differentiable solution here. So to prove this differentiable solution, you actually need Arzela-Ascoli. Okay, because I gave you a fixed function. Maybe you can do it. Okay, you go and integrate it, and then you differentiate it. But in general, how to do it? Okay, in general, how to do it. So in general, you need to use the differentiable definition, the limit definition. Okay. So you somehow need to so I put this is just a proof sketch. Okay, you can look at the notes that I posted in Moodles by Hutchinson. Okay. So basically they relies on this compact set here. Okay, and then define a piecewise linear function that can approximate the real function. Okay, and then it forms a Lipschitz family of function. So you can use Arzela-Ascoli to show that that's the um, sequence that converge to that function. And then we show that X is the required solution. Because this piecewise function here is differentiable. So uniform limit of a differentiable function is differentiable, right? If I'm not wrong. Correct or not? Okay. Luckily, I think I kept the note. Let's see. This is what we did. I think we make a table last time. So where's the table? Yeah, so let's see. If converge uniform, does it? Actually, no. Uniform limit of C is not differentiable, but I think, let me see, under some condition, maybe it's differentiable. Let's see. Point-wise convergence and uniform convergence don't preserve differentiability. Okay, let's see. Anything we can comment about differentiability or not? Oh, okay. So here it is. So uniform limit of a differentiable function might not be differentiable, but if you can control the derivative, okay, such that the derivative also converge uniformly to something, then this function is this limit here is differentiable. Okay, so if you can control the derivative some more, then the uniform limit of a differentiable function is differentiable. Okay, so just now, how we approximate the function is using piecewise function there. Okay, so the derivative here should be well behaved. Okay, yeah. So we don't write down this analysis proof because analysis proof is very tedious always. You need to check a lot of things. Yeah. Okay, so uniform limit of a differentiable function might not be differentiable, but if at the same time you can control a derivative, okay, to be uniformly converged, then the limit really have a derivative here. Okay. So you need to control two things. Okay. Yeah. To talk about uniform convergence of a derivative, differentiable function. Okay, you don't just want f to be uniformly converged, but you also want the f prime to be uniformly converged also. Okay, makes sense. I think this table is quite useful. This table here. This table quite useful. Okay, so continuity actually will uniform convergence will implies will preserve continuity, will preserve boundedness, will preserve unboundedness also because it's a complement, will preserve uniform continuity, will preserve integrability. I think if you forgot anything, this one is one of the things you should remember. Okay. Not preserve differentiability, but if we have an extra condition on f prime and also will converge to differentiable function. So you need to control two things for differentiability. Not just control function itself, you need to control the derivative of f. Okay, hopefully you still can recall back your memory on this MA thing. Okay, so OD have a existence theorem now due to Arzela-Ascoli. Is it true? Joshua, is this true? Is this what you learned there? Is this what Tao Shen tell you? Huh? Existence theorem. Does it need Arzela-Ascoli or not? Huh? You cannot remember. Sorry? Picard-Lindelof. What's Picard-Lindelof? Oh, more stricter. So is the you mean like for like this example case? Is it the least strict one? This one, this strict case. Okay. Yeah. Yeah. More. Yeah. Yeah. You can go for Arzela-Ascoli that tells you the existence of the solution. Yeah. So the Picard is what here? Okay. Any question before we take a break? The master has been disappearing for like two weeks already. Not sure they will appear tomorrow. No. If not, then we will call a day earlier tomorrow. Hello. Okay, let's take a break until 11:07.
uniformly 的一个反应模式。
应该是可以推出来的。
可是你用的一直是，但是我 proof 里面用的都不 uniform，
没有啦，我是说它可以推出来，
应该可以推出来，
从 equi continuity 推出来。
推出来。
嗯，
可是你的 proof 里面都用的是 uniform 一个。
我就说可以推出来啊，就是 like 加上其他条件，那个 equi continuity 会变 uniform 一个。
哦，Wikipedia 好像说的是 uniform，
真的吗？不可能。
哦是吗？哦，Wikipedia 说的这个。
现在应该是 compact 加上 equi continuity 就会变成 uniform equi continuity，对吗？因为在 continuity 的 case 也是这样嘛。你 continuous function 如果你把它缩到 close interval 的话，它就是 uniform continuity。 虽然 e/x 不是 uniformly continuous 在零那里，但是不可以这样讲，就是我应该讲啊，就是靠近零的点不是 uniformly continuous 嘛，但是如果你把它切掉过后，切在很靠近的零点，它肯定也是 uniformly。会讲话啊，不要讲话，少讲话，很重起来。现在也不要去看医生，吃那个 antibiotic 比较快。好，对啊，因为那 clinic 外面就有啊，那个厦门里面。或者后果啊，对，哦，嗯，这我看医生要跟妈讲啊。哎，去学校那间你们要给钱吗？哦，要啊，多少钱？哦，我以为你们有那种保险啊，不用给。这样的话，你去政府啊1块钱吧，要等一下，好像要去到 cyber 还是不 tra？这应该有啊，对你哎，我发现啊，为什么那个宗教仪式要这样？因为他们 provide 我安全性。比如说那个佛祖的顶华一粒，就是在华为的区，拜访。One of the reason, important reason，咬一层也是生病。virus。
Everything about it is okay. The fact that it's a vegetarian. Yeah.
所以你知道他 vegetarian，
妈妈告诉我，
他没有去妈妈，不是？
本身去跟的，然后他讲，然后我讲这个薯片好吗？不是讲自己做的，他讲不会设计个，就是vegetarian 的嘛。
你讲那个 global，
是的，
他只是味道吧？
味道好吗 ？Messi
哦，OK，嗯，
因为我早上看到是
啊哈，啊啊，是
我们学校里面没有人
是吗？
不要不接受，
哦，不给不，
那就
要这样提，OK，
自己用水死掉。那你看着你会觉得男生
对呀，说蛮感，
有钱，
是啊，肯定啊。那你不有钱，他车 BMW，哦他妈妈来的那天晚上能够专心做数学的只有钱人吧？啊？什么？不是我有钱了，我上面有点钱，可能 maybe。你是说 control positive？ Interesting. Okay, let's quickly finish it, then we can go for lunch earlier. Okay, so this is the last part. We want to generalize the idea of Arzela-Ascoli to a topological space. Okay, so we talk about topology now. No metric space. Okay, so there are three kind of topology here. Okay, so first is a pointwise convergence. Okay, so you should know from the Euclidean space what is the pointwise convergence, right? What's the pointwise convergence? Pointwise convergence. So you check at every point, okay? Basically, at every point will converge to a function, the limit f. And then second is compact convergence. This one maybe is a bit out of your idea. Maybe you never thought about this compact convergence yet. The last one is I even never thought about is a compact open topology. Okay. So all these topology will put on a space of function. So we denote at y superscript x here. So it's function from x to y. And we also put it on continuous function. So we restrict to continuous element inside here. So let's talk a little bit what are these three things and then how they are connected. So given one point in a x, your domain, sorry, and then codomain open set inside of codomain y. Then we collect all the f. Okay, all the f. How do we collect it? basically we just pick all the f such that fx living inside U lah. Okay, so we will put it inside this set here. And then we claim that this set is actually a sub-basis for topology on Yx, which is the topology of pointwise convergence. Okay. Think of it makes sense or not? So these are the sub-bases. So these are the set we declare open. Okay, so I pick one point X, I pick one open set U. Okay, I choose all the F such that the F should map this X into U. So you see this F already depends on this point X. So there's something to do with points. Okay, and then we will say that this topology is a pointwise convergent. So we don't make it using, we don't create it using basis, using the basis where it's a sub-basis where. So here we consider what? Union of finite intersection. Okay, are open inside the space here. Okay, so a typical basis element about the function f will be consisting of all function g that are close to f at finitely many points. Make sense or not? Because finitely many intersection. Okay, so if you want to talk about a basis element around an f, so who are around it? Okay, look at this construction of s, x, u here. So these are all the functions that are close to f at finitely many points because we take finitely intersection of them. So if we view x as an index set, okay, then the point open topology or the topology of pointwise convergence here is exactly the product topology actually. Okay, it's actually a product topology. Okay, and then the theorem here is if a sequence of fn right converges to a function f in a pointwise convergent topology, if and only if for every x in X, the sequence fnx of points of Y converges to the point of fx. So this is the reason why we call this point open topology here as a pointwise convergent. Exactly because this, yeah, because it's really equivalent to say that you have pointwise convergent. Okay. But the proof here is really similar to the proof of convergence in product topology. Okay, so this is the first topology. Second topology is the uniform topology on the function space, right, will guarantee the uniform limit of a continuous function to be continuous. So the question is, can I work out any intermediate topology between pointwise and convergent? So I repeat, between pointwise convergent and uniform topology here, such that we still have this result. Okay, something limit of sequence of continuous function is still continuous. Because in MA, you know that pointwise convergent doesn't preserve continuity. Uniform convergent preserve continuity. So is there something stronger than pointwise but weaker than uniform still preserve continuity? Okay, can we do that or not? So the answer is yes, actually. So this is what we call the compact convergence on compactly generated space. Okay, later we'll introduce this. So here says what? Actually, compactness is the key. Okay, compactness is the key because compactness will imply uniform continuity. Okay, so compactness here is the key. We need compactness here. Okay, so let's see how we introduce it. So if Y is a metric space and then X is a topological space, then given a function, okay, from X to Y, and a compact subspace of X, okay, and we pick some epsilon, then we'll define this epsilon ball here using F and C. So depend on the compact subspace. So just now depend on open set, right? So now depend on compact subspace. So what are these elements here? So these are other G such that the sup metric here is less than epsilon. Okay, then this will form a basis. This is what we call a compact convergence topology. Okay, so what's the difference just now? So just now here we got X, right? A point. Okay, and then C here is an open set. Okay, just now. But the open set is in the codomain, but now here is depend on Fn, the compact subspace. The claim here is this set will form a basis. Okay, then it will form a basis of topology, what we call a compact convergence here. So how do you imagine this set? So this symbol here is really important. What F is fixed. Okay, something very close to F. How close is it? This close. Okay, supreme using the sup metric. Okay, close with it. And then close within which area? The compact subspace. Okay, within the compact subspace, it is closed. Okay, so this is called a compact convergence. So you should imagine why we call it a compact convergence here. Okay, so remark here is if you compare to the point open topology, right? The basis element containing F here consists of functions that are close to F at all points of some compact set. Just now, just finitely many points. Now here is within the whole compact set, you are close. Okay, so why we give it the name? So here is the rationale why we give it the name, because it is equivalent to say that actually it's equivalent to say that every compact. So okay, so if Fn converge to some F inside this topology, right? It would mean you need to check that for every compact C, Fn restrict to C converges uniformly. Okay, uniformly to F restrict to C for every compact set. So that's why this is called compact convergence. So because it's uniformly convergent at every compact set. Okay, kind of strong, huh? Okay. Make sense? Okay, you need to check out, but we didn't check here. Yeah. Why is it weaker? Okay, later we will see. We will see that. Okay. Yeah, we will link that three together. Okay, later I will let you see what's the relation between the three. Okay. Oh, how is it weaker? You see, we only can check it for all the compact set here, right? For the moment here, lah. Okay. Yeah. If you are uniformly converged, I don't care where your x come from, right? It's for every x. But here is every part is uniform convergent. But turns out that this is enough already to talk about a limit of a continuous function sequence is continuous. Yeah. Okay. So next we'll talk about a topological space to be compactly generated. Okay. If it satisfies the following condition here, a set A is open in X if A intercept C is open in C for every compact set. Okay, so if your space is compactly generated, if and only if your open set intersect with every compact set is still open. Okay, it's still open. It's open in C. I think it's a subspace topology here. Sorry? That is what? Mm-hmm. Wait. Why are you talking about? So this is the definition of compactly generated. So you need to check a set is open in X if you take A intersect with every compact set C, it is actually open inside the compact set C. Yeah? Does it make sense?
I that in a subscript in a that in open space open is the open setting that the substrate.
If
I think this is a converse of it.
yeah, this is a converse of it. Yeah, this is actually a converse of it. Yeah, because subspace topology says what? Anything that open in the subspace if you take open set from X intersect your subspace, then it is open already. Okay, then yeah, then this is the let me think. It's open. Here you intercept first.
Open X.
Yes, right. Here you intersect first. Okay, so this is the compass here. Yeah. So it makes sense, because the open set in the subspace tell you what's open inside X. So completely generated. So what's open in the subspace actually open in the whole space. Correct? No? If you know that it's open in the subspace topology, then actually U inside the original space is open. Okay, so it's like really generated. So from the subspace, you already somehow know who are open inside the largest space. Okay, so the theorem here is if X is compactly generated, okay, so meaning you can use the open set in the subspace to talk about the open set in the whole space. Okay, you can like somehow, can I say pull back? Yeah, I think we can say can pull back or not. I think can pull back, but it's like projection. Okay, then let Y be a metric space if a sequence of continuous function Fn converges F in the topology of compact convergence, then F is continuous. Okay, the limit is continuous in this sense. A bit restrictive, you see, we control the how a space X is actually compactly generated. But for the cases that we consider like Euclidean, they should be compactly generated. Like the picture we draw every time, right? We to check the subspace, we are like taking the open set in X and then we intercept it, and then it's open inside. But if you look at outside, it's also open, right? Actually, the set we started with actually open, right? Okay, so this proof. And then what's the relation between pointwise uniform and compact convergent? So they are really a subset inclusion here. Okay, so when are they coincide? You see where are they? When are they coincide? In general, you have this chain here, but when are they coincide? So if X is compact, then this two is the same. If X is compact, then these two really is the same thing. Uniform convergence meaning implies compact convergence. Topology. If it is discrete, then the last two is the same. Okay. Okay. So the last part here is, let me see here. Is it the last part? 1, 2, 3, 4, 5. Yeah. Okay, the last part here is, you see, for the point open topology, right, we didn't say that Y have to be a metric space, but for uniform and compact convergence, we need the epsilon thing. But can we get rid of it or not? Can we not talk about supremum metric? Okay, can we not talk about it? Okay, so here it is. So let X and Y be topological spaces, no metric space at all. If C is a compact subspace of X and then U is an open subset of Y, then we define XUC. Okay, similar construction is like combining what we had for point open topology here. So we take all the function f such as FC is in U. Okay, so previously we are taking Fx is in U, right? So now we are taking the F of compact subspace. Okay, to live inside. And then this set will again form a subbasis like what you do for point open topology. This is a topology on function space. Okay, so this is what we call a compact open topology. Because we are using compact set to define it. Previously, we used point open topology. So now we use a compact set to define this topology. Okay. So the remark here is the compact open topology is finer than the pointwise convergence topology. Okay, it's finer. Meaning it contains pointwise topology, pointwise convergence. It's a point open. No, it's a point compact. How to get the pointwise convergent? It's a point compact. A point compact or not? Is one point set compact? Is one point set compact? Huh? Compare? Why? Closed bounded. Totally bounded. Huh? Okay, good. Okay, good. Okay, good. So there's only one thing you can pick there. So on the set of x tilde and yd, actually compact open topology is equal to compact convergence topology. That's why they share the same adjective here. Okay, so meaning if your y is really a metric space, whatever we do now is nothing. It's the same thing on what we had before. Okay. So the corollary here is let Y be a metric space. The compact convergence topology on CXY does not depend on the metric of Y. Actually, doesn't depend. Okay, although you said I did nothing. Actually, I did a lot of things. This means what? P actually useless. Because why? The definition of compact convergence topology, I didn't talk about metric. So if you change any D, doesn't matter one. Okay, doesn't matter. Doesn't depend on D. So this is a nice thing about abstraction. No D involved now. No metric. Okay, just the topology induced by this metric. Enough already. Topology, get the topology, then throw away the metric already. Okay. So then this is the final thing I'm gonna show you. The last of the last theorem of this whole week 15 class here. Okay. So Arzela-Ascoli theorem in a general version. So let X be a topological space. Okay, so D here, Y here we still consider as a metric space. And then if we give this CXY here a compact convergence topology, and then let F be a subset of this continuous function from X to Y. If F is equicontinuous under D, and the set FA here has a compact closure, okay, for every A in X. So this FA here basically is just you fix an A, okay, and then you look at how F apply, all the F apply to A, and then you look at the closure. Then F is contained in a compact subspace of C. Okay, the converse hold if and only if X is locally compact. Full stop. Yeah, this is the most general version of compact subset here. Okay. Yeah, any question? Maybe you could ask hey, where the bounded thing go, bounded and what else, close where do they go? Okay. So I think they should hide inside here. And what you prove here is F is just contained in a closed it's a compact subspace here. But if F is already closed, right, it is actually closed in a compact set is compact, is it? How does a closed react with compact? Then yet, do you remember how close react with compact? Huh? Close and compact is compact. Okay. And then another one, complete. Complete react with compact or react with closer. Yeah, this is a few things you need to keep reminding yourself. Did I remind somewhere? See, did I remind it somewhere? Yeah, these are the few things that you want to keep remember. Let's see. Compact in Hausdorff is closed. Okay, compare in Hausdorff is closed. And then close in compact is compact. Yeah. Okay, turn out that the converse version of Arzela-Ascoli theorem is harder. You need X to be locally compact. Okay, which is something we talked about last time about neighborhood being compact. And then Hausdorff, only you can prove the equicontinuity bounded those. Okay. Hey, why Manchun is here? Hello. Oh, you finished your monitoring. Okay. Start from 11? What do you mean?
You finished, right?
Oh, you finish in half an hour, you mean? Okay. I see. Okay. Yeah. Okay, so yeah, so for 15 weeks, we have do about 670 slide. Yeah, congrats to you. Turns out to be more. Other class turned out to be more slide. Okay. Any question? Any question? 仙丹 for what? Anyone know how to fix a sore throat? Himalaya salt must be from Himalaya. Just kidding. Google 它现在有 Google 诶 ，Google 眼水 ，Google 啊，讲他进啊，
这里光个啊，
啊
你还能够
，OK，记下是吗
这有打错啊？
？OK，不会吧？妹妹，考试考到哪里？OK，so very important 啊，where's the exam? Exam go up to see before storm check competification. So where is it? Just now I found it already. If 25 lecture 25. 26 is about storm check. No. Okay. Lecture 25. So there's no help in this final exam. So you need to internalize the definition here. Yeah. Yeah, that one you need to G. Yeah. 不然我花这么多时间一直跟你们讨论干嘛 ？Yeah, I think okay. Now 我们先直接 revise what is healing? What is healing? You got 2 points, and then one of them have house is enough. The other may be homeless. T1 both got house, but it is a semi-detached house. Could be a semi-detached house. The intersection could be non-empty. Okay, T 还有什么 T2 bungalow 还没有，我们到 bungalow 还没有 T2，T2 是 bungalow，T2 hostel yeah bungalow T2 is hostel right okay so 2 points got 2 open set cannot intersect each other intersection is empty yeah bungalow 2 bungalow okay bungalow 是啥独立屋 yeah 独立屋还有 T 什么来着 T3 T3 then upgrade not just 1 point already, right? 2 point. We talk about 1 family and 1 point. 1 close set and 1 point. Okay. And then T4
two family
two family. T4 two family. Yeah. Two closed set. Yeah. 就这样吧。T3.5. Yeah. T3.5 is what? Separate a point and a closed set using a function. Yeah. But I think more importantly is not this definition also. I need to know how they are linked. So which one imply which one imply? 感觉好像是没有 T5 的。But you got something called T2.5. 哦，有啊。T5 and C6 是什么来的？ complete 是什么？又是用 function 来分开。Okay, maybe got I don't know. But I saw got T2.5. Yeah, very constructive. 对，不是很重要的那个 proof， 也考不了那种 proof。Arzela
就可以啊，一个考试，一个考卷就问
作文，
在任何
写作文。
很直接。
啊，
那是 zero extension。
然后这样子包 domain open set。
没有那个 work 是因为我们来的，所以那个他讲的是 zero extension 就是这样。因为二边手边奇奇怪怪，是零
哦，
最好的，所以做 zero extension 让你 extend 出来是零，所以你可以怎样去搞？
等于你这边有个domain 呀。
对，
因为你那边不是 continuous extension， 你那个就是都丢一堆很零的东西。那个 Arzela 是它的 technicality 就是我在 continuous extension 那边，你怎样能够 construct 一个 function， 它又 continue。所以那边是比较麻烦。Yes。OK， 还有什么问题吗？我应该会在 revision 之前改完你们的3个 assignment。啊？你什么？你那么快？那里会快？我1个星期不是交回给你们2个，那时候没问题，很慢哈。除非我不吃不睡那边。
就这样，他写100分 OK 了。
啊？没有啊，就在你们 revision class 之前，因为我在想一下要讲安排要讲改。我希望1、2、3、4明天会改完，然后拜5、拜6我要去玩，玩完回来礼拜天又要玩。礼拜天我们有打球啊，如果你们有在的话，下午2点。And then 我就要改完 Topology 7、8、9，没有8、9、10。And then 要开始改 CH， 我也是感觉会改很快，因为就是3题短短的嘛。希望可以赶快。那时候我们没有介绍，你就用那个 Seng 这样。对，不够。我明天会讨论，OK。我明天会讨论。还有你上次跟我讲那个，你已经递到出来吗？你想一下，明天我还会再讨论。如果那个 point 有 hit 到，你就可以跟我讨论了。我明天会讨论，明天我们讨论5、6、7。对 ，Ultra Filter， 你知道 Ultra Filter come out in the 3个礼拜的 talk， 3个礼拜。 Yeah，因为我看到你有 define 在那边，but 就因为我们还没有介绍那个东西，不是你没是好事，但是你没有 verify 还是个 strong check configuration。你看过我们讲介绍 strong check configuration？是啦，你就要 prove 给我看哦，除非你把整套，因为那是新的东西，你要证明给我看那个是你讲的东西嘛，不然你写一个 strong check 我不知道什么东西啊。你确实有说哦，这个是 ultra filtration，然后这个是 strong check，但是你没有告诉我为什么它是 strong check，它是什么 strong check 是什么？那时候我们没有介绍这个东西，你知道要 check strong check 其实是蛮麻烦的一件事啊。3.6是吗？七是啊，我也是觉得。对呀、
没有发生是礼貌，
没有他要用它，他就是要把那个当做他的当做来。对，其实那题是蛮难的，那个 example 我扣你几分？1分，是不是？因为我知道那个 example 很难，所以我没有扣人家很多分。好像只有 Ray 他找到那个来比较 standard 的，等下有找到。也用 Tick Note 的东西，Tick Note 可以用啊，因为我们介绍了。呀，Stone Chain 是我们上个礼拜来介绍过，其实是一个很简单的一个东西啊，蛮。哎，那天你坐在这边听不是？我记得你在，他不在，不是你在呀？那个没听 OK，你要介绍给我，除非我介绍给你啊，然后你就，或者你要介绍给我，就是我班上没有 prove 过什么东西，你全部要 prove 给我，是吧？问题是我也没有说一定要那个答案嘛，但是如果你要用的话，你肯定要。
他是为了你着想，
我着想还是他着想？
自己给他背辛苦，这样可以快一点。
呀，But anyway，呀，那个是很难那个，因为那个 counter example 的话是要讨论是，你要同时 compare，然后不 sequentially compare，所以很难找对啊。
因为首先所有的
Yeah。耶，对，是蛮难找的那个，对，所以那一题那一题你没有注意到那个用词有一点怪呢，好像又不太数学这样，就是那个问问题的方式啊，我不是叫你 prove 或 disprove 吗？反而我是叫你找 flaw 还是什么找问题，找你觉得有问题的，但是没有教你 try to disprove 它嘛。如果叫你 disprove 它，你没有把那个 context 写出来，你就是0分了，对不对？所以对，有时候你要看一下题目有点 tricky，
问他就是标题有一点是吧？
对，你可以给一点，对，没有错，还在，不然的话肯定是死了嘛，proof or disproof 嘛。他们有拿满分吗？呀，有那个就 OK 啊。呀，那个我也没有要求他们真的去 prove 它 compare 是什么，I mean like，不是啦，I mean like，有 prove 啦，就是用 t i c k e t 来 prove 这样。OK，还有什么吗？几点了？啊，几题？什么 final paper？你讲那种 p a s s 哈？没有，没有 p a s s
那些都扫到了，
大家都什么烧完？什么叫烧完？
没有关系的。
没有啊，我才教过第2次吧？啊没有，不知道，不一定。为什么？呀、没有啦，I mean like 我就是在班上已经给你们了，跟我讲的一模一样的，你再去问也是一样的，是一样的东西。 有几题啊？好像是6题吧，如果没有错的话。Yeah. 嗯，Yeah Yeah.
就话给他
什么？什么意思啊？没有，你要有信心一点，
两
要有信心。
有的变很
因为都没有把自己规模。
你 pick，你要 pick 什么？哦，pick 啊。上次有啦，上次有讲 AG 的东西，因为 AG 还没有开嘛，现在 AG 也开了。AT 哈，AT 你就今天下午来哦，那个同学会讲关于一点 AT 的东西。
那的话，那个心脏让我想说，
我行
让对哦，也有人啊，那个敏感，
也
我想说，要是我发给人，然后拿个心脏出来，我要怎么办？
绑他，
这一段是什么？
昨天
因为那个公司的比赛，他们照这样把那个照片放进去。
然后
对
OK
这样子
yeah well I mean general topology 啊，跟 algebraic topology 其实是还有差别的，还有差距的。
还有联系吗？
有联系啊，不可以讲没有嘛，因为他们都有 topology 的字，but I mean the technicality 来讲的话，很不太一样啊。那边是比较 more on group 啊，然后你 construct 那个 space 啊，用点、用线、用圆圈、用 this，啊有 topology 在吧？不是这种 open 啊什么 close 这种 technique 啊，我是说那种 involved 的 technique 很不一样啊。技巧啊，学的技巧，algebraic topology 是一个全新的一个门课啊，明来。如果看过你们学的数学啊，什么？他配要3天圈哦，OK OK OK yeah yeah yeah。So algebraic topology，我觉得啦是 undergrad 里面最 top 的一门课。我不知道你怎么去定义它了吧？我觉得它是一个最 top 的一门课，最高级的。不是，不可以这样讲，不可以这样讲，不可以这样讲。就是这一门课是 analysis 跟 algebra 的精华，还是个精华。algebraic geometry 的话，你可以讲是难，但是它如果你要讨论它难，它的难可能是另外一种境界的，就是这样说哎，
可能给你中风。
啊，algebraic geometry 啊。因为你有时候看到它又很简单，它难的东西其实就是 substitution 来 substitution 去，或者 function 来 function 去。它虽然它的概念很难，但是它计算就是你看过的东西，对吗？像昨天我们讨论那个 LD 啊，其实你去算那个 vector space，就是你中学都会啊，怎么这样切一下 simplify 吧。但是algebraic topology 是新的 technique
因为我觉得
technique 来了，你没有看过的算法呀。chain complex 啊，什么啊这些东西，homology 啊，你没有中学没有看过这种东西的。但是 algebraic geometry 虽然说概念很难，但是其实你拿出来算的话，就是 substitution 啊，什么 change of variable 啊，然后 s not si 什么切一下就这样吧。但是 algebraic topology 是不同的 technique，chain complexes 啊什么，然后很 involved 的，比如说 linear algebra 啊，什么 modules 啊，我们那边叫。因为我们不一定是活在 field，我们通常都是用 integer 的，yeah。所以我觉得 algebraic topology 是一个最 high class 的课。如果不要让你的钱浪费的话，你一定要拿这门课。就开始对课，一定要拿这门课。这门课是数学系 undergrad 来说最 top 的一门课。你也可以想象它很难，但是它就是一个你最值得学，在这个 throughout 这个 undergrad 最值得学一门课就这门。我没有讲它容易，但是，yeah。嗯，对啊，对啊，对啊。
这里又不懂。
你很常会不懂啊。 所以麦克阿蒂亚很常讲一句话嘛。麦克阿蒂亚，你知道是谁吗？一个很出名的一个在 Oxford 吧，一定啊 ，Professor， 他讲 algebra 啊是魔鬼给 geometer 的一个玩具，他让你一直玩 algebra，你忘记了 geometry 在干嘛啊？所以就应验了你刚才那句话，做不进去。
反正就是你要理解你做了什么话，你中风了，
不会了，很多人都没有中
中风了。
啊。对对，是这样子啊。你很容易消失在 algebra 里。把这个是，把这个同时是 geometry 的一个语言。没有在我什么？
哎，是的，哎，就是做怎么没落到那个algebra里面。
哦，对，对啊。但是 geometry 就是 speak in algebra， 你是说 algebra 可以解释这个 geometry 的干嘛？algebra topology 是一个很新的概念了。对啊。还有什么课？你看下个学期啊？我感觉没有哎。最接近的应该是 differential manifold， 最接近的。Yeah，differential manifold 是有一点就是 differential geometry 的进阶版哦，就是也是进到 algebra 的程度哦。geometry 的话，可能你就 curvature 啊。其实，在我的 calculus 2，我 skip 掉这些东西了。比如说你有 curvature 啊，有什么 portion 啊，I think 那个转弯啊东西啊什么之类的。Yeah，什么像 physics 他们用的什么 stress 啊还是什么之类的这些东西，那个 curve 的多它的弧度多大。但是 algebra topology 算是一个蛮新的东西啊。对于你们来说，我不是说这学科很新，这学科应该也蛮久了。但是这个不是 something that we instill student 或 pupils 在below secondary 啊，没有。Not even university 啊，也没有。这种数学你是没有看过的，很神奇的。呀，我觉得你要毕业应该要至少拿这个。OK，但是也没有也不用紧了，没有也不用紧啊，也不用紧，不用紧啊。但是我是说，你拿了这门课，你不会怎么样？你一定物超所值，肯定。I mean like 现在的数学，I mean 至少纯数来说啊，就是都是在建立在 algebra topology 这上面。Yeah， 你拿了这门课过后啊，你觉得你的世界会不一样去？一样啊，就是一样，因为他们是同个 level 的东西。Yeah，AG 我觉得还好，就是像因为我刚才讲的东西，因为你到计算的时候，你还是在用你以前会的东西，其实也还好，但是你还没有去到 AG abstract 那个部分。但是你还没有碰到它，你就觉得很难啊。但是还没有到那个阶段啊，其实我们还是在蛮 basic 的。你觉得我的计算你觉得你没有看过没？check zero set 啊，check intersection 啊，这样。其实 AG 很 abstract 的地方，我也觉得很 abstract，我也知道。But algebra topology 的计算你是没有看过。New technique 啊，我只能说 is a new technique。fundamental group 啊，这样子啊，base of loops 啊，
就是你答应我们不要让他折磨我们。
我什么折磨？我什么折磨？怎样折磨？好像折磨，那折磨
现在 A 就有3个没有估量，
很难咩？OK，他讲难就很难了。Yeah， So I mean like F1 你拿去给那个 Imperial College 看一下，问他那边的 assignment 有这样的吗？啊，你问他看。
很高问题也比较难的。
哎，他那天讲你们做的很好啊，不是？不是哎，他那天讲你们做的很好，他也能做的很好哎。那个啊，阿瑞法讲你们那个班啊，啊，对，好是哈，
Yeah.
啊，OK，
他也是同时。I
okay,
think some of them don't know what they're talking
yeah,
about.
definitely, yeah.
OK 啊，至少我懂我在讲话。
At least.
Good. Okay, so see you tomorrow. Okay, tomorrow we got presentation and then we start on the assignment. And then we will take a group photo.
Master 哦，20